So let us talk about scaling. So what this actually means is now again, right, we have to be able to show that, that those equations that you saw earlier, xt is equal to some a times ax and yt is equal to a times, what is that, a times ys, right? That's what we had. That was a notation that we had used. So we had assumed that there is some a, right, that is there. So we want to actually show what camera motion and what kind of a plane normal, how the plane should be with respect to the camera, so as to be able to yield a motion like that. Right, so for that, what we will do is we'll kind of look at the situation where it's a fronto-parallel plane. Okay, so it's like 0, 0, 1. Okay, and you have a translation vector of the camera. Now the camera has to move, right? So the camera will now translate along the optical axis. So your tx is 0, ty is 0, and then you have only a tz component. So it's like saying that you have a camera like that, and you have a fronto-parallel plane because n is taken to be 0, 0, 1, and now you're right, you're kind of say translating about the optical axis. There's no translation like that, right? It's only going along the optical axis, and then r will be identity, right? We're not going to rotate or anything, so r is going to be identity. Right? Under these conditions, we'll show that we'll end up with those equations that we saw earlier. Okay, so what that actually means is that now let's again go back and okay, and then until now, right, I've been assuming that f to be 1, by the way, okay, all along. I don't know whether I explicitly told you that focal length, I've assumed it to be 1. In reality, right, I'll talk about that a little bit toward later on, okay. That matrix is actually a little more complex than what I've said here. We'll not kind of go into the full details and all, but I just wanted to kind of say touch upon the fact that the intrinsic camera matrix is a little more complicated than what I've assumed till now. Just for understanding sake, I kind of I try to keep that away for the time being, right? So our k is identity right now. So all that we are worried about is r plus, right? So we are sort of assuming that k is identity. So we are just looking at r plus 1 by d Tn transpose, right? So this yields you 1, 0, 0, 0, 1, 0, then 0, 0, 1 plus 1 by d. Now t is 0, 0, tz, there is only a z component, and then there is an n transpose which is 0, 0, 1 because it's a fronto-parallel plane. So under this condition, you will get 1, 0, 0, 0, 1, 0, 0, 0, 1 plus this will be 0, 0, 0, 0, 0, 0, and then 0, 0, tz by d. Right. So add the two up, and you will get 1, 0, 0, 0, 1, 0, 0, 0, 1 plus tz by d. Okay, now act this on some xs, ys 1, right, in order to know where it goes. Okay. So your xt, now this will be equal to, what do you get? Xs, ys, and 1 plus tz by d. Okay, which means that if I want my real image coordinate, okay, because it's still in a homogeneous, right, we're dealing with homogeneous coordinates. So in order to get my image coordinates, I should scale. Okay, my xt, yt that I really need, the actual xt, yt that I need are, xt will be then xs upon 1 plus tz by d, right? This I told you already. You have to divide by this, the third component, which is dz by d, and yt will then be, that means on the image image space, right, on the image grid, it will lead to a coordinate where yt is equal to ys upon 1 plus tz by d, and imagine that a is, let a be equal to 1 by 1 plus tz by d. Okay, then what this means is that you've got like your, so we are kind of back to that equation that we talked about, a times xs, yt is equal to a times ys, and a is of course 1 by 1 plus tz by d, and the tz being, if tz is actually, if tz is less than 0, that means if it is negative, that means you're coming closer to camera, then clearly a will be kind of greater than 1, which means you will be zooming in, Of course, the maximum that you can come as TZ negative will be like till you can come up to D, right? Because it's D away. After that, you will actually hit the plane itself, right? So TZ negative can only go till D. Then on the positive side, if TZ is greater than 0, yeah, you can have TZ. You can go as farther away as you can, and right, you are going away from the camera. Closer to plane. Okay, not camera. Closer to plane and away from plane, and you got A less than 1, which is zoom out. Okay, and yeah, so the idea was that at that time we just assumed that, right, there is an A, and we didn't really bother about where was that A coming from, what will influence A, and so on. But now we know that, what camera motion and how the plane should be in order for you to be able to see something like a scaling, okay, happening. Okay, these are small examples. Now I'm going to leave it as an example. Show, right, this is going to be a small little homework for you. Show what camera motion and what plane orientation will yield shear. Suppose you assume it to be like 1K01, this is like the X shear. Okay, what plane orientation will, we also saw, no, shear I told you was a special case of affine, right? Affine is like ABCD TX TY 001, right? But ABCD, if they turn out to be special like 1K01, then it's an X shear, right? So I'm just asking you because this is exactly the example that I gave in the class last time. Imagine, right, this you should be able to show by simply imagining the case where you have a car, right? Imagine that, right, this is your x-axis, you're kind of looking out of the car, right? So the camera is pointed this way. So the camera optical axis, so Z is this way, Y is down, right? Imagine that you're moving this way, so the camera is sort of translating along X, and then it is actually looking at this kind of ground plane. So the ground plane is actually below the camera, and you are actually imaging the ground, right? So what camera motion, and so I just want you to write up the correct normal and the correct T, R, well, right? I don't want to give away the answer, whatever it is, a small little answer, right? You can just figure it out. And so what camera motion, what plane orientation will yield shear? Okay, now let me put of the kind 1K 01 001 001. Okay. So again, right, so this is again going from the homogeneous to the things that you saw when you considered very simplistic cases. Okay, now what we have not talked about until now is the fact that, how do you really arrive at this homography now, right? Here I'm just assuming that somebody gives you all of this, right? In reality, if I give you two images and then, right, taken from the same camera, and I ask you to relate the two views, right, find out what homography will take you from one to the other. Okay, nobody will tell you what. No, somebody doesn't sit there and tell you, right, that this point is going there and that this point is going there and so on, right? Somebody told you, of course, it will be easy, but then in general, you can't sit and do that, right? So solving for the homography. Let's do solving for homography. There is also a special homography which is a rotation homography. What we are looking at is really a planar homography. So rotation homography I will do later. Okay, for the time being, okay, I'll stay away from that. And one more thing. Okay, let me just mention that. Yeah, maybe at this point of time. Okay, right, I'll also mention about this intrinsic camera parameter matrix. See this K, right, that we had taken, okay, we had said that it is F00, 0, F0, 001, right? This is actually a very, very simple situation, okay? Normally, okay, the way this K looks like, the real intrinsic sort of camera parameter, camera, this one, okay, this is called the intrinsic camera matrix. Intrinsic, because it's intrinsic to that camera, right? It stays unchanged. Intrinsic camera matrix, The other one, right, that you had, which involved R and T, which was the camera motion, right, that is called the extrinsic camera matrix, because that is not inherent to the camera. You can take a camera, move it the way you want, right? So it's extrinsic. This is intrinsic. So in reality, right, what you really have is something like fx, s, ox, then 0, fy, oy. Yeah. But this is only for information. So what this actually means is, so in a real camera, right, you're kind of assuming that when you put f0000001, what you're assuming is that the optical axis, right, it coincides exactly with the image plane center. Okay, it need not. Okay, the optical axis of the lens, right, when it passes through the image plane, right, we are assuming when you put the 0, 0 right here, this 0, 0 means that, right, you don't have any kind of a deviation. It's exactly, it meets the center of the image plane. In case it doesn't, and if there is a drift, right, then this OX and Y, no, these are again things that nobody may be able to give you, and these are supposed to be estimated. Okay, so that's why it's called a calibration procedure. Okay, we are not going to go into that, but typically if you want to use a camera, then you should know these parameters. If you're just doing a homography, you don't need any of this. Okay, that is also something that I want to emphasize, that if you're just solving for a homography between two images, you don't care about all these intrinsic parameters and all. All that you need to see is that matrix that is going to take you from one to the other. But if you want to do some high level tasks and all, like for example, if you want to take a camera, you want to estimate depth, 3D depth and all that, then in that case, this intrinsic camera information you need. Okay, so solving for this, so right now, right, we are assuming that K is of this form and F is 1 and so on. So OX, OY is like deviation from the center. This is like a deviation from the center. Okay, or in other words, center, okay, of the center of the image plane. Okay, deviation of the optical axis from the center of the image plane. From the center of the image plane. So we just typically assume that it coincides and so on, but it need not. Okay, there could be some errors, right, when they actually manufacture. You could get a small shift, right, so that you have to account for. There's fx and fy, right, this is supposed to be the aspect ratio. So normally the focal length is not really, so we'll assume that it's ff. But fx and fy, they write, right, what they really mean is if there is an aspect ratio, right, if there is a difference in the aspect ratio, then this fx and fy will take care of the aspect ratio. And this s is something, right, that actually takes care of deviation from what you call a rectangularity. This is something like the shear, this s, this parameter is something like a shear. Exactly like if you relate this to what we had, right, when we were doing the homography, right. So S is exactly playing a similar role, except that this is like a hardware thing, right. So this is like inside if the sensors, if there is some kind of deviation from a rectangularity, then this S is but this may not happen in the sense that you may simply, if there is no deviation, S will be 0. But if there is, then it needs to be accounted for. So this is like deviation from rectangularity. Deviation from rectangularity. So these are things that if you look at K, typically, right, it'll be of this form. So it'll have a kind of phi unknown sitting inside it. But as far as we are concerned, and anyway, right, since it's an upper triangular matrix, you see this, right? This is an upper triangular matrix, and you know that an upper triangular matrix is always invertible as long as the diagonal elements are non-zero, right? And fx, fy, and all are, you can relate them to focal length or the aspect ratio. So basically, none of these entries is 0, right? So this matrix is always invertible. So that K inverse that I kept writing it for f00 situation. But the same thing is also valid even if you take a real intrinsic camera matrix where maybe there are some other entries that you need to account for. There's no issue. Okay, there's always invertible. There's an upper triangular matrix with non-zero diagonal entries. Upper triangular matrix. In fact, there's also the reason why why let's say when these people do a camera calibration, right? Have you heard about a QR decomposition? In matrix, right? There's a QR decomposition. What does it do? It kind of, gives out a matrix as a product of an upper triangular and an orthogonal matrix, right? So that upper triangular is this K guy. That's the way they do the camera calibration. And then the orthogonal matrix is your R. R is an orthogonal matrix, right? So just saying that, so people do all this camera calibration and all. There are kind of nice ways to do that. Right? So upper triangular matrix always invertible as all its diagonal elements are non-zero. Elements are non-zero. Okay. Then now, right, let's kind of come back. So what we are saying is we have this. So we said that we have x dash, right, which is this homogeneous coordinate of your target, right, and we are saying that the h acts on x, right, where let's say x is the source. So x is like x is y is 1. So if you think about it, this is like I'm just going to write x because I don't want to carry this ss always. So right, this is like applying the homography on the source grid, and then it takes you to a target grid, which is x dash. Okay, and in order to get back your so in fact, right, I will even multiply this by lambda, just to indicate the fact that when you do hx, the even third entry here, right, it need not always be 1. You can end up with some lambda, which you'll have to use to divide the first 2 entries. So you have something like lambda x dash, right, is equal to h times x. Okay, this is what you have now. The point is, if you look at your homography, right, h, let us say that h has the following entries, h11, and this could be the case that you have an intrinsic matrix also sitting there, right, whose values you do not know any of these parameters. Let's say you have this most general case. Okay, it is still valid because all that we are saying is this h is some k, right? So h is k r plus 1 by d Tn transpose, and then what was it? K inverse, right? So we are saying that let that k be there, whatever it is. Finally, right, I just need to map this image onto that, right? As far as the homography is concerned, I am not worried about what the intrinsic parameters and all, because all that will get absorbed in my h. Okay, but if you want some other task and all, you can't always ignore and move on. Okay, you may have to go back and look at what is my camera, what are its intrinsic parameters, but yeah, right. But for a homography, it doesn't matter. So now what we are saying is, so let this h11 be let this h be h11, h12, h13, h21, h22, h23, h31, h32, h33, right? And we said that h has 8 unknowns, right? You can only estimate it up to the scale factor, and okay, which is anyway being shown here, right, by that lambda. So now since there are 8 unknowns, right, and so what this means is that you need at least 4 feature correspondences, because one feature correspondence. Okay, now right, I mean, in order to see that, right, let's start writing. Let us say that I have an image, okay, here, right, and then I have a source, and then I have a target. And suppose somebody says that, well, there is one point here that matches, that goes here. Matches in the sense that I know that, right, that this, imagine that probably, right, this is a corner of this one table or something. And I can kind of identify that corner in the second image. Now, this is not typically done manually. So what is done is typically you use some feature descriptors. Okay, you use what are called feature descriptors, and there are several of them. In fact, right, people have spent a whole lifetime, right, trying to find out what kind of features are good to match. So I was saying that right, you have these 2 images, and I mean, right, so like I was saying, there is a lot of work, right, which has actually gone into trying to match features, because, right, that is one of the fundamental things that you need in several applications, especially when you're trying to solve for a homography, because, right, if you try to see, right, what is happening here, you have 8 unknowns sitting in that homography, and if you had 4 feature correspondences, then it will yield you 8 equations. I'll show you why. Okay, so let us say that you have lambda, right, x dash y dash 1 is equal to h, which is h11 whatever, right, and then you have x y 1. Right. So if you just expand this, you will get lambda x dash is equal to h11 x plus h12 y plus h13. Okay, that's what is sitting in this h. Then lambda y dash is equal to h21 x plus h22 y plus h23, and finally you have lambda is equal to h31x x plus h32y plus h33. Okay, which then means that I can do lambda x dash by lambda, which will give me my x dash. So that is h11x plus h12y plus h13 upon lambda, which is h31x plus h32y plus h33. Similarly, we have lambda y dash by lambda giving y dash is equal to h21x plus h22y plus h23 upon h31x plus h32y plus h33. Okay, so if you kind of cross multiply, right? So what will we have? We will have okay, I'm going to write this as h31xx dash plus h32yx dash plus h33x dash is equal to h11x plus h12y plus h13, right? And from the other one, you will get h31 xy dash plus h32 yy dash plus h33 y dash is equal to h21x plus h22y plus h23. Correct. So now the unknowns we know are these h11 to h33, right, sitting there. So what we can do is we can in turn write this matrix, right? So we can write it as, let me go with the standard notation. Okay, so that is like, so what we will have is minus x minus y minus 1. So I'm trying to get all the terms on one side. Then see, so here, right, assume that you have this matrix multiplying h11, h12, h13, h21, h22, h23, h31, h32, h33, right? So you can just put all your unknowns onto this particular say vector, and we know that this vector needs to be found only up to a scale factor, right? So minus x minus 1. So if you see, right, so what have you got? h11 x, therefore if you pull it to the left side, it will become minus x, then h12 is getting multiplied by minus y, h13 is getting multiplied by minus 1, then h21 nothing, right? So 0 0 0, and then h31 is xx dash, right? h32 is yx dash, and h33 is x dash. And similarly, what you will get for the other one is h11, there is nothing, right? So you have like 0 0 0, and then h21 minus x minus y minus 1, and h31 is xy dash. So this is x into y dash, right? These are all coordinates that you are multiplying, y dash and y dash. Okay, this whole thing is equal to 0, correct? So now the point is, right, see, so all these entries we know, okay, these are all known quantities. It is all known to us, because when will it be known? When somebody tells me that this point is going there, right? Because I've assumed that somebody has given me a correspondence between x dash and x, right? Somebody has said that if you apply h on this xy1, it will take you to x dash y dash 1, okay? So which then means that with just one point correspondence, I have two equations, right? And since I have 8 unknowns, I will need 4 point correspondences. So somebody has to give me not just one, but people have to give me at least 4 point correspondences, so that I can solve for h, because h has actually 8 unknowns, and it is known up to a scale factor, right? So then you can kind of think of this as, you can add an x1 now. So you can say that for let's say one feature point, you have x1, y1, x1 dash, x1, x1 dash, y1, x1 dash, x1 dash, x1, y1, x1, y1 dash, y1, y1 dash, y1 dash, and similarly, right, follow it up with minus x2, minus y2, blah blah blah, right, 0 0 0, and go on, right? So you'll have x1, x2, x3, x4. So you'll have 8 rows minimum. You can of course use more, right? So this whole thing we can write this as A multiplying H equals 0, where 0 is again actually a vector. So A is 8 cross 9, H is 9 cross 1, 0 is 8 cross 1. Okay, so 0 is a vector, it's not a scalar, right? AH equal to 0. So this is also called a homogeneous least squares. Right, so what you're asking is, now the point is that you might ask us, who will kind of give me those point correspondences. So I was just talking about that. So basically, right, people have spent a lot of time trying to get these correspondences, and there are various things for that. So one is called, there are various such features that, let's say, people have found out. One is called a Harris detector. It is called a corner detector, Harris corner detector. Something called SIFT, which is a scale invariant feature transform, stands for scale invariant feature transform. Then there's something called SURF, which stands for speeded up robust features. And there are kind of many of them. Okay, now among these, SIFT is the one that is most common. Okay, this was actually proposed by a guy called David Loeb. So this is the most common, and the nice thing about this is completely translation, rotation, and scale invariant. And scale invariant, and it's partially invariant to illumination and pose. So what this means is that even if you have a pose change, right, it will still be able to reasonably identify that it is exactly that point. Okay, so it can tell that between these two images that you have, it can. So if you run a SIFT code, okay, this is available. In fact, when you do the assignment, we'll give you that code. So in this in this course, I don't go through the entire details about how SIFT works and so on. When we do a vision course, computer vision course, there we do. But here, just right, keep in mind that there are many such things that can allow you to identify feature correspondences across images. Okay, and SIFT is one of them, and it's pretty fast, and it's used it's used all over. But these are all called handcrafted features, by the way, right? These are not your deep learning kind of features. These are all handcrafted. Somebody figured out that if you do this, if you do a Gaussian scale space, right, and so you do some scale space processing, you will be able to identify features. So it's like saying that if you had a scene captured under some illumination, you capture the same scene after some time from a different viewpoint, but then even with a slightly different illumination, you'll still match those correspondences, and you will still be able to tell how the two are aligned. What geometric transformation can bring one to the other. Okay, so we'll assume that there is something like a SIFT available with us, right? Which will kind of, so you can just run it. We'll just give you that code. You can run it. You will see that it won't just pick 3 or 4 and all. You'll pick many. Now, the point is, right, for us it looks like if I had just 4 feature point correspondence, I'm done, because right, A being 8 cross 9, and as long as you make sure that no 3 points are kind of collinear, okay, then you can be assured that, right, A has a rank 8. Now, which actually means that because of the fact that, right, AH equal to 0, that means there is at least one kind of non-zero vector, right, which vector, okay, that is mapped to 0 by A, right, because A is 8 cross 9. So you know that there is at least one non-zero vector that is mapped to 0 by A. So one way to do it is you do a simple SVD. Okay, so if you use MATLAB or something, right, you will ask for null of A, right? So you'll say null of A. That is that one-dimensional vector, right? Which one? That's a one-dimensional space, right? In which this particular vector lies. All scaled kind of versions of that are okay. So when you do null of A, so typically what MATLAB does is it will do an SVD on A and then pick that eigenvector corresponding to the smallest singular value, the zeroth singular value, in fact, right? Because you know for sure that, assuming that all of these are, right, in this case we are assuming that you don't have 3 points lying on a line and so on. So you just have to avoid those things, but otherwise you can just pick any of these 4 points and you can run AH equal to 0, ask for null of A, and that will basically return an H for you, which is non-zero, which when acted upon by A will actually yield you the 0 vector. Now you can also clearly see that if you have any scaled versions of H, right, that will also go to 0, right, because A alpha H is nothing but alpha AH, right, and but then alpha, but then AH we know is 0, so this is like alpha into 0, so this is 0, right. So all scaled versions of H, so you can only estimate H up to a scale factor, which is fine, because as we said originally, we have only 8 unknowns in H. Anyway, right, we are okay with estimating H up to a scale factor, right. So whatever H that is actually returned is what you can directly use now. Then you can actually align the images now. So that H, you go back and put it back in your H matrices H11, H12, H13, H21, H22, H23, H31, H32, H23, H33, and then if you multiply it with any x y1, what will happen is you will get actually a 3D vector, that is a 3-dimensional vector, and this need not be 1. So you'll have to scale the first two by this, and that will give you the image coordinate.